Hello everyone, my name is Mihal Brunduli from Pragmadev, and this talk will be about automatic verification of BPMN model. The work was done in collaboration with Emmanuel Godin from Pragmadev also and Cyprien Teodoro from Insta Bretagne. So first a few words about BPMN and the context of this work. BPMN stands for Business Process Modeling and Notation, and is a modeling language standardized by OMG, or the Object Management Group. It's a widely used language to describe interaction between different participants in a complex organization. It describes the possible sequences of tasks executed by several participants to fulfill a specific mission. BPMN is used to describe a wide variety of systems such as air traffic control, for example, satellite constellations or armed forces coordination. BPMN is used by the French Army and its main suppliers to describe the interactions between participants involved in a mission. And this work is part of the Verimode project, which is a research project financed by the DGA, aiming at developing a tool that will help users to verify their BPMN models. Some real use cases were also provided by Eurocontrol and Airbus Defence and Space. So as BPMN models become more complex, it is necessary to ensure their functional correctness. It is common practice, for example, to gather all the different stakeholders in a room and review the operational scenarios captured by the model. During these review sessions, the model is typically corrected and refined until it captures unambiguously all stakeholders' requirements. However, these meetings are time-consuming and error-prone, of course, because the model interpretation is performed by humans. To address this problem, we propose a tool enabling semantic-driven model manipulation and verification. The BPMN model correctness should be ensured at three levels: syntactic, semantic, and logic. From a syntactic point of view, the model should adhere strictly to the standardized BPMN notation. From the semantic point of view, the interpretation of the model should be captured formally and unambiguously. This way, we can have means to execute the model, for example, step by step, to debug it, profile it, and so on and so forth. And finally, at the logic level, the model interpreted through the semantics should correctly capture the mission of the systemic models. We address these correctness elements by performing a static syntax check, first of all. Then we have the possibility to execute the model interactively. We can also record and replay different scenarios, and also by means of the verification part. So the outcome of this work is a BPMN viewer and editor. Of course, it is necessary to perform all the other tasks at hand. Then a BPMN executor that implements the standard execution semantics found and described in the standard in the OMG standard, and the BPMN explorer for model complexity evaluation and also for property verification. The tool, so the outcome, was used to check correctness of the provided use cases by the DGA, Eurocontrol, and Airbus Defence and Space. So in the following slides, I will talk a little bit more about the model executor, first of all, and then go a little bit in the details of model exploration and property verification. So starting with the model executor, so each BPMN element in the model has a state of execution, and depending on its state, it may accept actions. So an action can change the state of an element during execution, and this action can be either an enabling or a disabling action. Since an element can be enabled or disabled several times, meaning that many flow of execution can go through a given element, then each BPMN element has actually a list of states of execution. The current execution state of a BPMN model is composed of the execution states of all elements in the model. And possible execution states are none, active, ready, enabled, and disabled. So during execution, the most recent state in the list of state of every element is displayed in color. So let me show you a little bit how it looks like. So at every step of execution, the user interacts with the model by enabling or disabling active sequence flows, message flows, or process call activities. So user actions actually will update the execution state of the model and make it advance a step further. As execution advances, it will define a scenario. So basically the flows and the elements we went through the execution. And such a scenario can be recorded in a message sequence chart. So it's a sequence diagram. These recorded scenarios can be replayed later on the model without any user interaction. So the first step is to have an interaction with the model step by step. So the user is responsible for defining the scenario of execution by interacting with the model. Then we can record this sequence of steps and then we can replay it. Why is this important? Because this feature can be used actually to check for non-regressions in future evolutions of the model. So having a basic idea about how execution works and how the executor is organized, having each element having a list of states and possible actions are proposed at each step, we investigate the idea to actually verify the model in terms of exploration, meaning that so that we can explore all possible execution paths of a given model. Our verification tools usually come with their own language and associated semantics, which are different from the one used to model the system. So to verify a model, the usual process using these tools is to translate the model to the verification language. But since the underlying concepts may differ, we may end up with a twisted version of the model. One of the innovative aspects of the observer-based prover that we use in this method and in our tooling is that it relies on external model execution that is compliant with model semantics. So basically, OBP, or the observer-based prover tool, does not know anything about the model. It does not even load the model. It leaves this task to the model executor, whose semantics and way of functioning I described in the previous slides. OBP focuses on the analysis of execution with respect to the logical properties. In OBP, the property to be verified is a logical combination of elementary properties. And the logical structure is understood by OBP, but the evaluation of these elementary properties is forwarded or is delegated to the model executor. So OBP, to control the model execution during a verification, can retrieve the global state of the model execution as shown in the picture, in the slide, set the global state of the model execution, collect the possible next steps of execution, execute one of these given steps, and then so on and so forth. So basically, OBP controls in a certain way how execution advances. But the whole execution semantics is implemented and handled by the BPMN model executor. So having a basic idea of this architecture and the communication between the BPMN execution engine and the tool that handles the actual combination of properties, we ended up in some problems that we had to address during the exploration of the model. BPMN may look simple, but actually it's not so simple. Mainly because of the gateways that may create some unexpected or very complex behaviors. For example, in the picture shown here, this is one construct that we saw in our use cases. In this example, the end symbol is never reached by all flows due to the implicit forking gateway in task 2. There are no explicit gateways in that example, but at the exiting the task 2, there are two flows, unconditional flows, which means they will be always executed, meaning that the upper flow will be always executed, so we end up with an infinite loop in that case. So this poses a problem, of course. First of all, for the logic of the model, we have a model that we cannot actually terminate execution. And second, very important for verification, is that we have a loop that executes indefinitely, creating many states, so we may have a problem of an infinite states during verification. So one possible solution, which is the other picture, is to introduce a conditional sequence flow, for example. This conditional flow will break the cycling of the loop conditionally for the user, for the logic of the model. However, from a verification point of view, it is still a problem, because following that sequence flow and also the loop is still a possibility during verification. So in this case, what we did is to actually limit loop execution to one iteration. So basically all the loops are iterated 0 times and only once. Because for us, from the verification or model exploration perspective, is a symbol or element or flow coverage. So this one does not affect the actual results. And the second example is the black box example. So usually, as BPMN models become complex, there are several teams responsible for different parts of the model. And if the team does not know anything of another part of the model, it may represent this as a black box in their model. So what we did in our execution engine is we proposed to the user to either load this black box, so go and find it where it is defined, or just ignore it. The simple fact of ignoring such a black box in the execution context means that all the message exchange, so we have to make a decision what happens with all the message flows. Our decision was, as we don't know the details of that black box, is to decide that all these message flows can be sent several times, infinite times, and every message flow entering the black box will be always received. This is the semantic. But having a message flow to be sent many times, it will actually create more or less the same problem of an infinite state space during verification. And in this case, there is no simple or logic solution, but just to define an upper limit for the number of message flows that can be sent. So, property verification. First of all, there was a question to decide how we'll describe these, the properties to be verified. Having a verification engine that can explore all the paths, so the next step was to define how we can describe our properties, and then use the verification engine to actually, in every given scenario, verify such property. So, since the BPMN executor produces execution traces, the trace diagram via message sequence chart, it sounded very feasible to use a property sequence chart for this, for expressing properties. So here we have an example of a client server, very simple example with two participants exchanging two messages, the request and an answer. The lower part of the picture, we can see a sequence chart with the same messages. The only thing that changes in comparison to a message sequence chart are the prefixes of these messages. The E part means that is a precondition. The R part means that the message must occur if the preconditions are met. There is also another prefix not shown here, is the F1. This means that in this case, whatever is prefixed by the F, it must not occur if the preconditions are met. So how we read this? This having a request message from the client to the server as a precondition. In all possible execution paths or scenarios during exploration, we should have an answer sent from the server to the client. Now, a second possibility that can express many more properties in a very complex way is the generic property specification language, which is the language used by the observer-based prover. So structurally, the GPSL specification is composed from a set of property definition, and the language delegates the evaluation of the atomic propositions, as I mentioned before, to the executor. And atomic propositions are strings of characters enclosed between pipes, as shown. So in this example is a representation of the same property but expressed in the GPSL language directly recognized by the observer-based prover. GPSL uses BPI automata for expressing temporal properties, and the linear temporal logic support is provided by synthetically extending the propositional layer with temporal operators. So, the property sequence chart notation is based on the work initially started at the University of L'Aquila in Italy. And in our case, we have adapted the transformation to generate beauty automata conforming to the GPSL beauty automata. So basically, GPSL, as is part of OBP, already is translated into this layer, automaton layer. So what we did is we plugged into this layer from the definition of the property sequence chart. And an automaton is composed of a set of state, initial state, an accepting state or states, and the guarded transition. So in this slide is shown the generated automata from the example before of the client server. So putting it all together, so it may sound a little bit complicated, but here is an example of this. So what we do is, through our tooling, there is a graphical user interface, of course, so we may launch an exploration of the model, or in this case, a verification of the property. So when we launch a verification of the property, we will have some feedback from OBP, and if in this case, as shown, the property is violated, we will have the possibility to actually replay the scenario that has given us this result. So if a property is violated, we have back from OBP the scenario, the counter example, which is replayed automatically in the model using the executor semantics avec the colors I described previously, and also having a message sequence chart trace, which we can save so that when we correct the model, we can replay the same message sequence chart. So, as an example, this is a very small part of an example coming from the DGA. It's called the closed error support model. First, we didn't have any properties defined to verify. So with no property defined yet for verification, the only result that we can get from this exploration was the number of possible scenarios or possible states of execution. So this basic information actually turned out to be very informative for the model complexity. Because if the number of possible execution paths is very large, compared to model complexity, it probably means that there is a problem in the model. So, and this problem is in this example, is caused by the implicit gateway at the entrance of the confirmed target task. This creates many flows in parallel, and it will result in more than 9,000 configuration states. Instead of 38, after replacing that implicit gateway, which is exclusive, with an explicit parallel gateway. This can be pinpointed. So the same problem can be pinpointed via a property. Here is a property that may identify the same problem described in GPSL. So if we launch the exploration and property verification function of the tool, OBP, of course, will say that the property is violated, and then we can replay the actual scenario that led to this property violation. So we can see in the picture that what we want is to authorize fire when both described target and described situation both are executed previously. But having that implicit exclusive gateway there means that we can possibly just follow one of the paths and not necessarily the other, which violates the property. So to conclude, the Verimog project was aiming at verifying BPMN models, and for that matter, a set of tools have been developed, including a syntax analyzer, a dynamic execution engine, and a tracing mechanism and a property verification engine using OBP. Even though the semantic of the language looked fairly simple at first sight, it actually contains very complex set of variations, and after analyzing the different use cases that we had at our disposal in the Verimog project, it turned out that most of the models were not correct. And this, the example I showed is one of the scenarios that we identified, for example, also with the verification part. Thank you for your attention.